So it turns out this equation we have for force only works between 2-point charges or spherically symmetric distribution of charge. So it will work if you have two spheres that are charged. It works just fine. Or it works if all of the charge is concentrated at a point. It will not work if, for example, we brought that demonstration in where we charged the rod up and then held it close to the little spheres. It doesn't work. This equation isn't valid for a rod of charge and a point charge. So we are going to look at another little concept that will allow us to more easily find the force when we have something like a rod of charge or something that doesn't fall in this category. Now, let's revisit gravity for a second. Gravity, we know, is an attractive force due to two massive objects. So objects that have mass somehow attract each other. We don't really know what the root cause of gravity is at this point. But gravity itself, let's say if we have the Earth, a person standing on the Earth will feel a force of gravity. That's considered their weight. So the force of gravity is pulling on the person, pulling them towards the center of the Earth. An airplane. Sorry, I'm artistically challenged. So an airplane flying above the Earth also feels a force of gravity from the Earth pulling it towards its center. The moon, very, very far away. The moon experiences a force of gravity, which is the whole reason it orbits the Earth, is because the force of gravity causes it to do so. The moon has a velocity which keeps it moving in its orbit, and the force of gravity keeps changing its direction, which is why it moves in a circular orbit. Okay. If somehow the moon were to disappear, would that change the fact that the Earth could possibly pull on something if it was there? So, took the moon out, would there still be an acceleration of gravity there?
Yes.
Yes. If we put the moon back, it's going to feel the same force it did. We call this effect here, basically the acceleration, we call it a gravity field. There's a potential over here for an object to feel a force. There's nothing there right now, but if we place something there, say a satellite, if a satellite happened to be there, it would feel a force, right? Right now there's nothing there, but there's still this potential for the force to exist. This is called the field. If we took the airplane away, there's still the potential for something there to feel a force. The field is simply the force of gravity divided by the mass of the object that we're taking out of the picture. So the mass of the airplane, for example, we can pull that out of the picture. The mass of the person, if the person wasn't standing there, there would still be this potential for a force to exist, but the person actually has to be there to feel the force. So the force is the absence of the object to feel the force. Another way you can think of it, imagine taking a bowling ball and putting it in the middle of a waterbed. It's going to put a dip in the waterbed, right? So the waterbed has this big old dip in it, but it's not exerting a force on anything else because there's nothing else around the bowling ball. Yet if you took a marble and you set it close on the bed, close to the bowling ball, and let it go, what will happen? It'll roll into the bowling ball. So it will feel a force, and that force will pull it in. Without the marble there, the bed is deformed. With the marble there, the marble feels a force. You can think of the field kind of as a deformation of the space around the object. The Earth deforms space around it, and objects feel forces if they're anywhere in that deformation.
It sounds kind of Einstein-y.
It does. That's kind of how they explain the concept of general relativity, the space-time business. That's the technical term. So with electricity, we look at things similar. If we had a charge, big old charge, it's going to deform the space around it. It's going to make a divot in the space so that if we had other charges nearby, they're going to feel forces. The electric field, so we called that one the gravity field. This was the gravity field. This is going to be the electric field because it's going to be due to electric charges. The electric field, we're going to use a capital E to represent it. It is a vector. It has a direction associated with it. Similar to gravity field being the force over mass, the electric field is going to be the electric force over the charge. We're going to call this charge Q naught. Your book calls it a test charge. Q naught, the test charge, is whatever charge is feeling the force. Okay? So if we place a little Q naught out here, do you agree it's going to feel a force because it's near this one? Let's call this one big Q. So big Q is the guy deforming space. Little q is the one feeling the force. So the force on this one, since they're both positive, it's going to repel. So the force will be pushing away from that other charge. If our little q was down here, our force would be away. If our little q was over here, our force would be away. If it was up here, our force would be away. Light charges repel each other, so that force is always going to be away. So the electric field is this potential for the force to exist. The electric field around a positive charge points radially outwards. It represents the direction the force will be in if we put a little positive charge in there. Okay? So electric field, by definition, is the direction the force will be on a positive charge that was placed nearby.
And that's merely the direction?
It's the direction, but if we know the strength of the electric field, we can easily find the force.
Well, yeah, because the force is going to, the magnitude of the force is going to vary with the size of the charge associated.
Correct.
So we can't just say, oh, there's a field of this strength. We can say, there's a field of this direction, but the strength varies with what's there.
The strength around this would vary, yes, depending upon where we were at.
Okay.
But if we knew what the strength was at the position we're interested in, then we're good to go.
Okay.
So, for example, if we wanted to know what the force would be on if I placed a charge there, if we know the strength of the field there and the direction of the field there, that gives us the electric field. If we know how much charge this little guy has, we can easily find the force that it will experience. Okay? So it is possible to find the strength of the field and to use it to find the strength of the force as well. Okay? The field, you're right, is going to change. Turns out, if we draw a bunch of these lines in, where the lines are closer together, so nearby this guy, the field is stronger. So the field is stronger, which means if I place a little charge in this region, its force is going to be much bigger than if I place it out here. Which should make sense. The closer we have them together, the bigger the force should be, just from this equation. Okay? So where the lines are closer together, the field is stronger. As they continue to radiate outwards, they get further apart, and so that's where the field will be weaker, which in turn, if this gets weaker, then the force gets weaker as well. Okay? It is possible to have a region where the electric field is constant, where it is uniform everywhere. It's not with point charges, though. Point charges, we can't get a uniform field. Okay. So the electric field represents the direction the force will be in on a positive charge. If you know the strength of the field, you can easily find the force that any charge would experience. You can rewrite this equation. The electric force will simply be the charge times the electric field. Now please notice I did not put absolute value signs around this Q naught. Okay? You need the actual value. What's going to happen if we put a negative charge in here?
The field's going to go the other way.
Okay.
Well,
The field's not going to. Okay,
charge.
the field, by definition, is the direction the positive charge would feel a force on. So whoever came up with this idea defined that to be the way. So the electric field depends upon this guy. So the electric field is still going to point radially outwards. But what can you tell me about the force if we put a little negative charge in there?
It's going to be attractive.
It's going to be attractive. When you put a negative value in for Q naught and multiply it by the electric field, you're going to get the opposite sign for the force. So mathematically, you want to put the correct sign that correlates to your little charge that's feeling the force. You want to put the sign associated with it in there. So this is not absolute value. Okay. Now granted, if we change the sign of this one, if this big guy that's creating the electric field were negative, then the field lines would point in towards it, because the force on a positive charge would be towards it. Electric field lines always point away from positive charges, and they point towards negative charges. Okay. It turns out there's actually some pretty nifty ways to find electric field around objects that aren't just point charges or just spheres. So it turns out we can find electric field, which will easily allow us to find the force without requiring both to be point charges. Okay? So this equation was limited in that they had to be point charges. This equation works as long as you know what the electric field is. By the way, you can find the electric field of a point charge like this by taking that equation and divide it by Q1 or Q2, and that will give you the electric field. Electric field ends up being K, a constant, times Q, big Q, over R squared, and it's a vector. Okay.
But R squared is dependent on the position of the reference
Right.
charge, right?
Exactly. R squared depends upon how far away you are interested from the guy creating the field. So you just need to know where it is that you're interested in knowing the strength of the field.
There's no magical quantifying value for a field. It's all dependent on the test charge.
Exactly. Well, it's not on the test charge. It's dependent upon the guy charging
Well,
it.
I mean, the distance of the test charge changes the electric field. The definition of
The distance away from this guy, yes. Exactly right. So yeah, that's what this R is how far away you are from the one that's generating the electric field.